Hello everyone. Exploring quadratic and exponential graphs is the focus of this video. What's our goal? We want to compare these graphs, exponential graphs and quadratic graphs, so we can further determine and understand the meanings of zero and negative exponents. So the big picture is exploring the two graphs. The very specific goal is zero and negative exponents. So as you can see on the left, we have, as you can see at the bottom, we have two graphs. On the left, we have a quadratic graph. You can see from the table of values that's given, and then you can see the plotted points, the vertex, and then if we go left, right, and right 1 from the vertex, we move up to 1, and if we go left 2 and right 2 from the vertex, we are up to 4. Because whether the base is positive or negative, when it becomes squared, x squared, it turns out to be positive. So negative 2 squared becomes positive 4, and positive 2 squared becomes positive 4, and thus the quadratic curve grows upward on the negative side and also grows upward on the positive side. Now the exponential curve, which we're going to first talk about the exponential curve, we're going to consider the negative and zero exponents, and then on the next page we're going to further zoom in on the meanings of zero and negative exponents. So looking at the table, 2 to the exponent 0 is 1, and 2 to the negative 1 becomes 1 over 2, and 2 to the negative 2 becomes 1 over 2 squared, which is 4. So as you can see, the more negative we travel in this curve, we actually end up with an answer that's a fraction, and it gets very small. It gets very close to 0, and in a later video, you'll discover it actually never equals 0. And as the exponent becomes positive, positive 1, positive 2, we start to experience some accelerated growth. Thus, this function, this relation, y equals 2 to the exponent x, if you notice the x is in the exponent, which means as the variable x changes, it will grow very quickly as we move to the right. And as we move to the left on the graph, it'll get the values of y will become very, very small. As you can see in the first two fractions, we have a half, and then we have a quarter. The next one's going to be an eighth, and then a 16th, and then a 32nd. As you can see, they become very small. Okay, so these are the two graphs. The exponential graph on the right with base 2 to the exponent x, and the quadratic graph on the left with base x squared. Okay, so let's further examine zero exponents now. Let's move into another page, and let's consider and examine zero exponents. Okay, and to understand the meaning of zero exponents, let's go back to our exponent rules. So if we had 7 cubed all over 7 squared, the division rule tells us to subtract these exponents because the base is the same, which leaves us to 7 to the exponent 1. If we put this in expanded form, which is just 7, if we turn this fraction, this quotient of powers with the same base into expanded form, there's 7 times 7 times 7, all divided by 7 times 7. And if we simplify our fraction, then 7 divided by 7 divides out to 1. 7 divided by 7 divides out to 1. So we're left with 1 times 1 times 7, which is just 7 to the exponent 1. So as you can see, that's how our exponent rule of division of powers with the same base works. So therefore, if we had 7 squared over 7 squared, the division rule tells us it's going to be 7 to the 2 minus 1, which is 7 to the 0. 7 to the 0. So the 0 exponent just revealed itself. What does it mean? Well, take the original division. 7 squared is 49, and 7 squared is 49 in the denominator, and 49 divided by 49 is 1. So therefore, we can make the connection that when the exponent is 0, the value of the power equals 1. Let's continue with that train of thought. So 7 to the exponent 0 equals 1. Let's do another example. 9 cubed over 9 cubed. Using the exponent rules of division, this becomes 9 to the 3 minus 3, which equals 9 to the 0. We have a number being divided by itself. The answer has to be 1, so we equate 9 to the 0 to equal 1. If we had a base of negative 8 all to the exponent 0, the answer would also be 1. So thus, the meaning of 0 exponents links back to division rules of powers, the quotient rule. And you have a power with the same base being divided, two powers with the same base being divided, so thus the exponents subtract and equal 0. And in number sense, in the idea of the actual numbers here, a number being divided by itself will always equal 0. The exponent will always equal 0. The answer will always equal 1. 7 divided by 7 is 1. 10 divided by 10 is 1. 9 to the 3 divided by 9 to the 3, which in exponential form is 9 to the 0, equals 1. Okay, excellent. Let's move on to negative exponents. And let's continue to use the division rule, the quotient property for dividing powers with the same base. Let's continue to use that train of thought because it'll help us with understanding the meaning of negative exponents. So if we take 3 cubed over 3 to the 4, you can see that the denominator has a greater exponent. If we expand this, there's 3 factors in the numerator, there's 4 factors in the denominator, 3 of them divide out. There's an extra factor in the denominator. So this answer becomes 1 over 3. Well, if we didn't expand, we would have 3, base 3, to the exponent 3 minus 4, which leads us to 3 to the negative 1. So if we simplify the powers, we end up with 3 to the negative 1. If we expand and divide and reduce fractions, we end up with 1/3. So we can make the connection that 3 to the negative 1 is actually 1 over 3 to the positive 1, which evaluates to 1/3. So negative exponents mean that when you had a division of powers with the same base, there were more factors in the denominator. The exponent is greater in the denominator versus earlier examples where the exponent was greater in the numerator and we ended up with a positive exponent. Okay, let's continue with this idea because there's a few twists. There's a few twists to this understanding. So let's consider another example. Let's consider something like negative 3 squared versus brackets negative 3 squared. Okay, so we don't have a negative exponent, we have a positive exponent. However, on the left, the base is 3. It's not negative 3. That exponent is only on the 3 and there's no brackets. So this would be solved as follows. You leave the negative on the outside, you put a bracket, and you deal with the 3 squared, which becomes negative brackets 9, and then you deal with negative 1 times 9, positive 9, which equals negative 9. On the right, the entire base is negative 3 because the exponent 2 is on the bracket. And if it's on the bracket, the entire contents of the bracket is the base. So therefore, on the right, it would be evaluated as negative 3 times negative 3, which is positive 9. So you can see there's two completely different answers because the bases are different. And the same idea with negative exponents. So if we had negative 4 to the negative 2, not only do we have a negative exponent, but we have a base that may or may not be negative, versus negative 4 to the negative 2. So on the left, the base is just 4. So leave the negative on the outside, put a brackets, deal with this as 4 to the negative 2, which becomes 1 over 4 squared, which becomes 1 over 16. Then multiply the negative back in, and it's negative 1 over 16. On the right, the base is negative 4. So this becomes 1 over negative 4 squared, because the negative exponent becomes positive in the denominator, and you bring the base down. On the left, the base is 4, so only 4 is brought to the denominator. On the right, the negative 4 is the base, and that base gets brought down to the denominator. And then when we evaluate, it becomes 1 over 16. So you can see we have different evaluated answers because the base was different. Even though they both had a negative exponent, you need to focus on the base as well. When you bring that negative power, the power with the negative exponent to the denominator, only the base gets brought down to the denominator. And if we examine this example on the left, only 4 was the base, and thus only 4 is brought down to the denominator. On the right, the negative 4 is the base, and that negative 4 gets brought down to the denominator. Wonderful. Okay, so now let's add another twist to this understanding of and meaning of zero and negative exponents, which relates back to exponential graphs, which allows us to compare quadratic and exponential graphs more effectively. Like I said at the beginning of the video, the specific focus here is zero and negative exponents, and we're going to use that idea in this lesson in the application of comparing quadratic and exponential graphs. But the focus of this video, the main focus, is understanding zero and negative exponents. So let's move on to the final part of this video, where we might have to solve for a missing value. So solve for n. So for example, something like 2 to the n equals 1 over 8. Well, the left side is 2 to the n. So let's separate it. The right side is 1 over 8, which we could write as 1 over 2 cubed, which we could write as 2 to the negative 3. So now both the right side and the left side appear as a common base. And that's a great strategy when you have to solve for unknown values. Common base. Write both sides as a common base and then equate the common parts. So now both left and right side are base 2, so we can equate the exponents. So therefore, n has to be negative 3. And that's what you would do when you have to solve for a value, either the base or the exponent, in these more challenging word problems where you're using your meaning of zero and negative exponents in an application of solving for a missing value. In this case, solving for n. So the opening question was base 2 to the n equals 1/8. So we take 1/8, write it as a common base, which is 2 to the negative 3. And then we can equate the left side with the right side, and we can drop the bases and just focus on the exponents since both bases are the same, and ends up becoming Therefore, n equals -3. And that concludes this video. Thank you for watching. You guys are awesome. Have a great day.